It's worth stopping for a moment now and to review some problem-solving strategies that we've been using to work problems where we've got forces and we want to use those forces to find the acceleration. And then if we have that acceleration, we can find position, speed, all of those kinds of things using the tools we already learned from kinematics. So I haven't laid this out explicitly, so I want to be fairly clear about this. So the first step in working with forces is to figure out what object you're going to be interested in and drawing a force diagram for that particular object. So for example, if I have an object here and I can figure out the forces look something like, let's say this, and then maybe a force like this, and a force off in this direction, then we can start to look at maybe what direction the acceleration is, and maybe even can tell something about what's going to happen. And so if these are our forces, then we can add them up and figure out, okay, do we have balanced forces? If these are all balanced, then we have an acceleration of 0. If they're not, then we're going to have some acceleration. So this, for example, could be an object on an inclined plane. Whoops, there's our dot, where this is our weight, our mg. This is our force normal. And then maybe something is pushing it into, force push, into the surface. And so, in fact, we might then use a tilted coordinate system for something like this. We'd call this the x, and then this our y direction, because we might be able to say something about the acceleration along the x direction and say there's no acceleration along the y direction. And in that case, then we're using trig to set up our coordinates. So what we're doing is we're doing a force diagram. We set up our coordinate system, so if possible, so that the acceleration is 0 in one direction, if we can. Just makes things easier. Then, once we have that, we may need to then divide things into components. Often we do. Components, this is where SOHCAHTOA comes into play. And then from there, we're going to use F equals ma for in the x and the y direction, for example. Okay, and from there we're just going to be doing some algebra, but you want to understand what these force diagrams are actually telling you. You can read information off of these force diagrams. So let's look at a couple of examples of how we can use this and even read some information or build some information into our force diagrams, depending on what information we have. For example, if we, and sort of our fifth step, I guess I should say, is we need to, of course, check our units. And then if it's a situation where we know something about how reasonable the answer should be, and then maybe check the size of our answer. Sometimes we just don't know answer size, but if we get a negative and we know we should have a positive answer, then we've gotten something wrong. So check answer size and signs, right? Or if we're supposed to find the weight of somebody and we find that it's so many thousands of newtons, and when we do the conversion we realize we've just said somebody weighs like 4,000 pounds, we probably did a calculation wrong. So that's the idea of checking whether the answer is reasonable, what makes sense. Okay, so let's do a situation where this is similar to what we saw before, what we set up. So we have one mass connected by a rope to a second mass, so these masses are the same. We're going to have a hand that's lifting these, that's holding these up, and we're going to say, in fact, that the hand, so this is the setup, the hand, so we have a hand up here, right there. Yeah. There's a thumb. Okay. Something like that. So we have a hand that's holding it up. The whole system, the block system is moving up, but slowing down. And so we want to construct this force diagram. In some ways, this is the hardest thing to do. Well, all of this description says nothing about what happens to the weight. We can still write mg and mg. What's going to adjust is our tension force, depending on whether we have acceleration. So moving up means that our velocity is up, but if it's slowing down, that means our acceleration must be in this direction. So that means our net force has to be down, which is a little tricky. So that means that if I look at this block right here, we need to have another arrow, tension up, tension on this block, but notice that tension's got to be smaller than the mg. This is how I'm drawing my force diagram. And then from that, the coordinate system will just be in the y direction, so there are not even any components, so I would just use F equals ma at this point. And then, of course, the tension on this is going to be the same. These are third law pairs. I'm going to circle them as third law pairs. And then the tension or the force of the hand, if you like, the hand force is going to need to be mg tension, but not quite as big as these two added together. So this maybe is force of the hand. So the hand force is less than this tension plus this mg together. So I've tried to draw it pretty much to scale, maybe just a little bit like that, okay? With the difference between these two set up so that I get the same value of the acceleration, whatever that number is. So again, this is how I'm building a force diagram, in this case when I know something about the acceleration. Let's do another situation just so we can practice doing this. So I'll set it up over here. Okay. The main thing I think people need to practice are force diagrams. You don't want to create extra forces, but you want to have enough forces. So this is a block on an incline. We're going to say there's no friction. And then there's this pulley that connects them. And we're going to say I have a mass 1 and a mass 2. And let's say that the whole thing is that it starts from rest and starts going down. So we have acceleration is in this direction and this direction for block 2. Okay, so M1 is significantly heavier than M2, let's say. Maybe I make M1 bigger. Okay, so it became bigger. So again, I've got an M1G that's down this way. And we know, again, because the acceleration is down, that this tension up is going to be smaller. That's my tension. It's up. It's going to be smaller than this. So that I can have a down acceleration, right? And then this tension has got to be equal to this tension here. Okay? Those are third law pairs basically on the rope. So that's the tension up. And then we still have an mg that's down. So I've got an M2G that's down that has two components, right? A component here and a component here, because we would use a tilted axis. Okay, coordinate system for this block does not have to be the same for the coordinate system for this block. This one can use its y-axis, but then I can say this is the x and y-axis for mass 2. And so when I look at this, I need to add one more force, right? And that is the normal force. So as I look at this, force normal, my normal force is equal to the y component of the weight. So it's equal to this y component of the weight. The x component of the weight right here must be smaller than the tension because I've got acceleration that's going uphill like that. And so if I write the equations associated with this, I break things into components, do F equals ma. This is theta, which sets this up by what we did before. That little angle is theta. So for mass 2, in the x direction, so x, the x component, I would have m2g sine of theta, that's the x component right there, and make that in the negative, plus tension is equal to ma, okay, m2, sorry, m2a. So that would be what would be happening for m2. That would be writing the equation using F equals ma once we've done our components with a tilted coordinate system where we have acceleration in the x direction. I can also write a y equation, but I don't need to in this case if I'm setting things up, if I'm given the acceleration. So m1 is only in the y direction. We'd say tension is up minus m1g is equal to a minus m1a, because a is down, so I'm putting this minus sign in, so both of these a's are exactly the same thing. The sign's already taken care of. If you're worried about it, you can give yourself an absolute value here. And so when we solve this, we could check our units. We could make sure if we were solving for acceleration that it did give us a positive value. Maybe we're trying to find the tension. Also should be a positive value because we've already put our signs in here. Okay, so these are the equations we would work with, and then we would solve depending on what the problem gave us. The point here is, these are sort of made up situations, right, is that we use these steps and we use our force diagrams. Our force diagram is what tells us what to put into our F equals ma. I'm reading values. In the x direction, have tension in the positive, and an m2g sine of theta in the negative. And so those tell me, though the balance of those forces tell me the acceleration. Over here I have tension up minus mg down. My acceleration is down, so I have a minus m1 times whatever the value of the acceleration is.